This is Module A7. We're continuing with Objective 11, starting with the states of consciousness. When we look at the states of consciousness, there are many gradations in those states. We find that the degree of wakefulness indicates the amount of activity that is taking place within the central nervous system. When that level of activity is abnormal or depressed, we find that the state of wakefulness is thus affected. Deep sleep, this is also known as a slow wave sleep, is when the entire body relaxes. The amount of activity emanating from the cerebral cortex is very low, and heart rate, blood pressure, the respiratory rate, the amount of energy being utilized declines upwards of about 30%. An alternate form of sleep is referred to as rapid eye movement, or REM sleep. And individuals who are in REM sleep are actively dreaming. We find that during these times you get changes in the blood pressure and the respiratory rate. I think we've all probably woke up startled from a dream, finding that your respiratory rate has increased. We find that we're less receptive to outside stimuli compared to when in deep sleep. Our muscle tone is decreased markedly, and we have an intense inhibition. Let me back up. An intense inhibition to the somatic motor neurons. Obviously, when we're dreaming, we're often very animated in our dreams, and we need an inhibition. We need to prevent somatic motor neurons so that we don't interact or act out those dreams physically. What the musculature that is not inhibited would be the muscles of the eye, because during REM sleep, the eyes move rapidly as the dream events unfold. In a nighttime sleep pattern, we see that there's an alternation between the deep sleep and the REM sleep. And the sleep pattern begins in deep sleep, and at the start of the sleep pattern, we find that REM periods last about 5 minutes on average, and as you move through the night, that increases to about 20 minutes as you approach 8 hours. Sleep has a very important impact on the central nervous system. It produces, it has no effect on the organs, though. Sleep is not required for the organs. There's very little physiological activity associated with the organs and the various organ systems. We do see that protein synthesis in neurons is increased during sleep, and that extended periods without sleep lead to disturbances in terms of mental function. It's been estimated that upwards of 25% of the U.S. population experiences some type of sleep disorder, and that leads to disturbance in mental function. Figure 1614 looks at levels of sleep. Here we have the actual activity, awake versus REM versus a deep. Slow wave, that's what this is, where it gets its name. The wave is very, the frequency is slow, so to speak. And then of course this bottom one looks at the various types of sleep on the Y with time on the X. And we start off and we see that we alternate throughout the night between REM sleep and deep sleep until you awake. The next system we're going to look at is the reticular activating system. This is something that was supposed to be introduced back in Module 6 when we looked at the medulla, but I kind of pushed it forward since it went well with this states of consciousness. The RAS, or the reticular activating system, is what deals with the transition between sleep and being awake. So it is the RAS system that actually awakens one from sleep. We find that it's relatively extensive. It's found ranging from the medulla all the way up to the mesencephalon. It's a diffuse network in the reticular formation, again, that ranges from the medulla up to the mesencephalon. And when the RAS is inactive, the cerebral cortex is also inactive. It's the stimulation of the RAS that produces an activation of the cerebral cortex, which then allows for consciousness and alertness. It ends sleep. Any stimulus that activates the RAS in sleep, whether it's a loud noise, whether it's light pouring in from the window, whether it's the smell of someone cooking breakfast, any type of stimulus that activates the RAS is going to end sleep. And we find that arousal occurs very rapidly. In fact, the effects of a single stimulation of the RAS last less than a minute. When in order to maintain consciousness, you have to have activity in the cerebral cortex. Not only the cortex, but also the basal nuclei and various pathways that stimulate the RAS. We find that after many hours, the reticular formation becomes less responsive to that stimulation. And the individual becomes less alert, they become lethargic, and the neural fatigue ultimately is responsible for reducing the RAS activity. Regulating the awake-asleep cycles involves an interplay between the brainstem and different neurotransmitters. We find that when the RAS is stimulated with norepinephrine, it maintains awake, or the alert state. Other groups promote the sleep by depressing RAS activity using the hormone serotonin. So it's an interplay between hormones that determines the awake-asleep cycles. It's the dueling, so to speak, of the different regions. But the interplay, the two hormones involved, or the two neurotransmitters rather, are norepinephrine and serotonin. This is the figure 1615, looking at the reticular activating system. It's a special sensory input, whether it's visual or auditory, all plays and into the reticular formation right here, stemming from the medulla up to the mesencephalon, and that is then going to activate the cerebral cortex and bring about consciousness. In Objective 12, we're going to look at the effects of aging on the central nervous system. We find that after about age 30, anatomical and physiological changes occur, and they tend to accumulate over time. 85% of people over the age of 65 have changes in their mental performance and the functioning of their central nervous system. We find that there's a reduction in brain size and weight. The cerebral cortex decreases in volume. Your gyri become narrower and your sulci wider. And your subarachnoid space increases in size. The number of neurons are reduced. As the brain shrinks, it's linked to the loss of the actual neurons itself. Do note that you do not get neuronal loss in the brainstem nuclei. We're talking about cerebral cortex here, cortical neurons. Arterial sclerosis, these are fatty plaque deposits on the walls of blood vessels. When you have a cross-section of a blood vessel and the formation of a fatty plaque deposit, what happens is you reduce blood flow through the arteries. This also weakens the wall of the artery, which increases possibility of a rupture. The cerebral vascular accident, or CVA, or stroke, can damage many surrounding tissues, and we talk more about CVAs when we cover the cardiovascular system in AMP2. When we look at the synaptic organization of the brain, we see that there are many changes. Dendritic branches, spines are all decreased. You get a loss of synaptic connections. And the amount of neurotransmitter that has normally been produced is decreasing. You can get the formations of plaques and tangles. Don't confuse this with the arteriosclerotic plaques that I just mentioned. Within the brain, we get deposits of several types of peptides. They're primarily two forms of amyloid beta protein, and they tend to appear in brain regions associated with memory processing. So as these beta amyloid proteins build up in these regions of the brain that deal with memory storage, they impede or inhibit memory storage. Neuronal processing becomes less efficient with age, memory consolidation more difficult, and it's more difficult to access secondary memories. In terms of sensory systems, you lose your hearing, your balance, your vision, your smell, your taste. I always remember my grandmother saying, "Nothing tastes like it used to when I was a kid." Well, of course not. You've lost your sensory systems. Your ability to taste has become less acute, along with every other sense system that is declining. Reaction time has slowed, and your reflexes, they weaken. In terms of motor control, you have a decrease in your precision. Often individuals who are older, they have trouble walking, mainly because of the precision is decreased. And it takes longer time to perform some of those motor controls. Incapacitation, 85% of the elderly population develops changes that do not interfere with their abilities. Some individuals become incapacitated by changes within the central nervous system, progressive changes. Senility, also called senile dementia, these are degenerative changes associated with memory loss, anterograde amnesia, and emotional disturbances. Of these, Alzheimer's disease is the most common.